to understanding the rest of this talk. I'll tell you what's important and just try to grab those concepts, and we'll reiterate them later as we go through it. So again, we're going to be talking about the physical layer. And if you think about the OSI data model that we've all seen, the physical layer refers to how your bits, your data, get mapped into physical phenomena that represent them in reality. And when you're dealing with wireless systems, that mapping maps the bits into patterns of energy in an RF medium. RF stands for radio frequency. And it's basically electromagnetic waves or energy that is just everywhere. And you can manipulate RF by using a device called a radio. And radios can either be hardware-defined, where the RF kind of mechanics and the protocol are baked into the silicon and are inflexible, or you can use a software-defined radio, where you have some very general flexible silicon up front that basically just grabs some raw information and feeds it to some sort of a processor, which can either be a traditional CPU or an FPGA to implement some of the more radio-specific things. And SDR has come a long way in the most recent few years, and it's now incredibly powerful. So we're going to be talking about both hardware-defined radios and software-defined radios throughout this talk. So if you put together a radio coherently, you can start to develop it into a PHY. And a PHY has one main component, or several components, but one of the main components is this notion of the modulation. And the modulation is the algorithm that defines how your digital values, your bits, are mapped into RF energy. And there are a few parameters that we can kind of tweak to do that, and those are amplitude, frequency, and phase. And then we can put them together and use some combination of them as well. And modulators can modulate either analog or digital information, but we're going to be talking about modulating digital information today. And an essential concept with that is this notion of a symbol. This is something that's very important to remember. And a symbol represents a discrete RF energy state that represents some quantity of information. So it's discretely sampled, and just think of it as being like a state in your RF medium that means something. And we'll illustrate this in just a moment. So here we have two pictures of two different modulations. And I just want to put these up here to help maybe get a grasp on what a symbol looks like. So on top, we have frequency shift keying, where you can see your signal is alternating between two frequencies. When it's on the left, it's dwelling on one frequency, and when it's on the right, it's dwelling on another frequency. Which symbol is present is based on basically what frequency that signal is on at a discretely sampled moment in time. So you could think of this as being like, it's a 0 when the signal is dwelling on the first frequency, the one on the left, and it's a 1 when the signal is dwelling on the right frequency, frequency 2. And you can see the analog with the bottom modulation on-off keying, where the signal being present represents a 1 and the signal being off represents a 0. So hopefully that helps you get a grasp of what it is that we're talking about. There are, of course, more complicated IoT PHYs. We have spread spectrum, where data can be basically chipped at a higher rate. It'll occupy more spectrum, but it makes it more resilient to noise. And then we have some technologies that do that, like 802.15.4 is one that uses a spread spectrum mechanism. So we talked a bit about radios just a moment ago. We're going to use two different kinds of radios when going through this talk. First, we have our hardware-defined radio, which is a microchip LoRa RN2903 module. And this is basically a dev board that has a hardware-defined LoRa radio built onto it. So this is going to be our transmitter that we're going to be targeting. And then finally, our receiver is this software-defined radio right here. This is an Edis USRP B210. It's just a commodity software-defined radio board. And basically what this thing does is it gets raw RF information from the air, serves it to my computer so that I can start to work with it with commodity tools like Python, NumPy, GNU Radio, things like that to start to process it. One last thing to cover is the fast Fourier transform. The fast Fourier transform basically takes a signal and decomposes it into all of the smaller signals or subcarriers that compose it. And any periodic signal can be modeled as a sum of harmonic sine waves. So basically, the FFT takes any signal and unravels it into the components. And why we care about this is it's basically a very easy way for analyzing and visualizing signals in the frequency domain. So when we take a bunch of FFTs and put them together, we get this picture called a spectrogram, where you have time in the ones that we're going to be looking at. I'll have time in the y-axis, frequency in the z-axis, and then frequency in the x-axis, and then power in the z-axis. So the intensity of the color is how powerful that component is at that instant in time. So here you can start to visualize all the different signals that are present. Okay, raise your hand if you're an expert. I see a few hands. Hopefully this is all that we're going to need. I'm going to reiterate some of these concepts as we go through, so I really hope this doesn't alarm you or send you running for the door. It's going to be very visual as we go through it, and hopefully the graphics will help keep this all grounded. So let's get into the meat of how this LoRa PHY works. LoRa uses a really neat proprietary PHY that's built on a modulation called chirp spread spectrum, CSS for short. Now, what is a chirp? A chirp is a signal whose frequency continuously increases or decreases. You can think of it as being like a sweep tone. And if we visualize it using a spectrogram as before, it looks kind of like this. In this case, we have a finite amount of bandwidth, and the frequency either increases or decreases. You can have up chirps or down chirps until it reaches the end of its band, and then it wraps around back to the bottom, back to the beginning, and continues. So here you can see that the frequency, the first derivative of the frequency is constant. So the frequency is always increasing or decreasing at the same rate, and then when it hits the end of the band, it just wraps and keeps going. So why use something like CSS? It has properties that make it really resilient to noise and very performant at low power. So all these things with IoT-focused radios and having very long battery life, these are properties that lend directly to that sort of efficiency. It's also really resilient to multipath and Doppler, which is great for urban and mobile uses. So this is an interesting set of features here. Where else do we see chirps? Radar is, I just heard it, thank you. Yeah, radar is a really common usage. And you'll see military marine radars will sometimes refer to chirps as wideband or pulse compression if they're using chirping in the radar scheme. And they're also used for scientific over-the-horizon radars as well. And there's an open source project called the GNU Chirp Sounder that has some features like that for visualizing these over-the-horizon scientific radars. And also in a past life, I worked on a scientific radar called SuperDarn, which is a similar over-the-horizon radar for visualizing ionospheric activity. Cool. So that's a little bit of background on the technology here. So this is kind of my journey into starting to work with LoRa here. In December of 2015, I joined this company, Bastille, where I am currently. And on the threat research team, we have these weekly meetings where we get together and we look at either new RF techniques or protocols, things that are interesting. And we basically just have a deep brainstorm on how they work and what's interesting. And the first meeting that I participated in, it was the first week that I joined, they were talking about these LPWAN technologies. They sounded pretty cool. So when we broke for Christmas, I went back to New York, where I'm from, and brought my radio and started poking around and seeing what I could find. And my colleagues looked in San Francisco, Atlanta, and I also looked in Boston. I was there too. And we didn't see LoRa anywhere in December. Fortunately, a few weeks later, I was at a meetup, and I encountered this company, Senate. I was living in Cambridge, Massachusetts at the time, and they were talking about their home heating oil monitoring network. It sounded pretty cool. So I looked them up later and was watching one of their marketing videos. And there was like a 2 or 3 second bit where you could see one of their technicians operating a computer, right? And they put up this picture. And this looks just like a coverage map, right? So, this could be fake data or it could be live. And I take a bit of a closer look, and I realize where that is. That's Portsmouth, New Hampshire. That's like an hour away from Boston, so there's really only one thing to do. So I hop in my car and I drive up to New Hampshire and Maine border, and there's me behind the wheel of my Saab with the USRP on the dash. And after about 10 minutes in the Marriott parking lot across the street from their headquarters, we have our first sighting of LoRa in the wild. There it is. That's the first signal I recorded. So let's take a closer look at what we have here. So if we look at the top third of the picture, we have a series of repeated upchirps. You can see the signal is just continuously increasing until it hits the band, and then it wraps and continues. And knowing what we know about digital communication systems, most of them have some notion of a preamble or a training sequence to tell a receiver that, hey, heads up, you're about to get a packet. So probably what that is. Following that, you can see the chirp direction changes right in the middle, and you have 2 1/4 down chirps. And this looks like a start of frame delimiter or a synchronization element. So this tells the receiver, hey, heads up, preamble's over, you're about to get the data, you're about to get the payload here. And finally, you can see the chirp direction again changes to be up chirps, but this time the chirps are kind of choppy. You see they jump around throughout the band just kind of arbitrarily. It's not arbitrary, though. That's actually the data being encoded into the PHY. So here we can see that the chirp frequency, that is the first derivative of the frequency, the rate at which the frequency changes, remains constant, right? However, the instantaneous frequency may change within the band. So you may have these jumps, but remember that the rate at which it's changing is always constant. You can just have those discontinuities. And those instantaneous frequency changes represent data being modulated onto the chirps. And you can kind of think of this as being like a frequency modulated chirp, where with an FM signal, you have a static carrier, at a fixed frequency that you're modulating to produce that signal, the modulated signal. Here we're modulating a chirp signal to produce that. So rather than having a fixed frequency that you're modulating this continuous chirp. Cool. So let's get our hands dirty. Let's figure out how this thing works and start to pull some data out of it. Before we dive into demodulating it, let's take a look at what we know through some open source intelligence. And using open source intelligence is a great way to really kind of shortcut the reverse engineering process, because otherwise you can wind up doing a lot more work than you have to. So there are a few things that were really useful, and we'll talk about these as we go through this material. First thing I found was the Semtech European patent application. It was in the EU market that basically defined a modulation that looked a lot like what LoRa could be. That's the number if you want to look it up later, but that had some pretty good information in there. Secondly, we have the LoRaWAN spec, and again, that's the layer 2 and up spec that's open, not the PHY, but it still has some references and defines some terms that are likely going to be analogous to the PHY, so still pretty useful. And finally, we have 2 application notes from Semtech that were pretty juicy. The first one in there, the .18 one, contained a number of reference algorithms for implementing a whitening sequence, which is like a scrambler. We'll talk through that. Or no, sorry, it's we'll talk about that momentarily. And then .22 had like just a general overview of the PHY and defined some terms. Also, there was some prior art online. There was a partial implementation in RTL Strangelove that didn't really seem to be maintained. It seemed pretty neglected, and I never really got it to do anything at all. But was still good to look at and had some really good hints in there. And then there were also some very high-level observations in the PHY in this wiki page, revspace.nl/decoding LoRa. And it was mostly just like looking at the spectrum and seeing that it's a chirp modulation and a few like example recordings and things like that. So from this documentation, we can start to pull out some definitions. Defined, we have the bandwidth, which is how much spectrum the chirp can occupy, the spreading factor, which is the number of bits encoded per symbol. And remember, the symbol is just an RF state, right? It's the number of bits in each RF state within the modulation. And then finally, we have this thing called the chirp rate, which we've kind of hinted at. It's the first derivative of the chirp frequency. So the rate at which that chirp signal is constantly changing. And we can pull some numbers out of this documentation to define those. So we actually have some common constants for the first 2, and then we find a formula in one of those documentations that states the chirp rate is a function of those first 2. And since there's a finite number of values there, we can start to iterate and just try all the different chirp frequencies and start to find one that works. So in this case, what is a symbol? Well, we've talked about how this modulation is basically frequency modulated chirps, right? So what we're going to try to do with this demodulator is quantify exactly where the chirp jumps to whenever we have one of those discontinuities. So let's start working through it here. There are really 3 steps we're going to achieve. We're going to identify the preamble, which is the beginning of the frame, denoted with the 1. We're going to find the start of the PHY data unit by looking and synchronizing against the sync word, which are those down chirps that are there. And then finally, step 3 is we're going to try to figure out how to extract the data from these instantaneous frequency transitions. And to do that, we need to quantify them. Now, there's a technique that I found pretty early on that was enormously helpful for doing this, and that is to transform the signal by dechirping it. And we'll show you what the result is in just a moment, but first we're going to have to do some math. And math is in red because it's scary, but it's not really. It's actually pretty easy. So there's a basic property of complex signals that states that if you multiply 2 signals together, the resulting signal has the frequency of each of the components added together. And from that, if we multiply a signal one frequency against a signal that has the negative value of its frequency, the result is 0. We get a constant signal. And we're working at baseband here, which means the center of the band is 0 hertz, so we can see negative frequencies and things like that. So if you multiply an up chirp and a down chirp together, what do you get? You get constant frequency. Now, why do I say constant frequency rather than DC? If the chirps are out of phase with one another, there might be an offset from 0 hertz there. So it might not be perfectly aligned with 0 hertz. We might and do expect to get some offset there. So what happens if you multiply a chirp signal like this separately against an up chirp and a down chirp? So you do two different operations, produce two different products. What do we think is going to happen? Well, if you do that, you get these pretty pictures right here. So here you can see those really kind of tricky diagonal chirp signals that are cutting all over your spectrum and are hard to measure, are translated into these nice, nice signals that are aligned in time, and that looks like something we can start to really work with and do something with. So we need to quantify those. So again, remember symbols. We're going to keep coming back to this. It's an RF state that represents some number of bits. And the LoRa has this value called the spreading factor that we found in some of the documentation that defines the number of bits encoded per symbol. And from the picture we saw a little bit earlier, the common values are 7 through 12, or 6 through 12. You see them both in different markets. So from that, how many possible symbols do we expect there can be? Well, each bit can have 2 states. It's a 0 or a 1. And there are spreading factor number of bits. So the number of symbols is 2 to the spreading factor. So how can we start to quantify these symbols and start to pull them out of the phi? So the steps that I found that were the trick to this were to channelize and resample the signal to the chirp bandwidth, dechirp the signal with the locally generated chirp we just talked about. Then we're going to take a fast Fourier transform of that signal where the number of bins of the FFT that we compute is equal to the number of possible symbols. And we'll illustrate this momentarily. And then, if we do that correctly, then the most powerful component in that fast Fourier transform, that is the strongest component frequency that we get back from that operation, is the symbol that we're looking for. So by dechirping it, we get it into a form where we really expect there to only be one strong component per FFT. Whereas if we didn't dechirp it, when we took the FFT of a chirp's worth of symbols, we would see the energy kind of spread all throughout all the different bins. But by dechirping it correctly, all that energy gets pushed into one bin, and we get a single clear value out of it. So if we do that, we get a picture that looks like this. And here, the z-axis again is the intensity, the power present, and we expect that to be the symbol that we're looking for. And here it's aligned in time with the base chirp on the left there. So here are the steps. Again, we mentioned this earlier. Let's look for the preamble, right? What's a stupid, simple algorithm for finding this? Let's dechirp it, let's do an FFT, and let's look for basically the most powerful component being in the same bin for some number of consecutive FFTs. Easy. Finding the SFD is the same thing, but again, this time we're going to do it on the opposite dechirp product. So when we dechirp it, we get back 2 different streams. We get one of the dechirped up chirps and one of the dechirped down chirps. So we can look at the opposite stream and do the same algorithm looking for the SFD here. Important caveat. Accurately synchronizing on the SFD is essential for getting good data out of this demodulation. Because if you have a bad sync, then you can wind up having basically your symbols, the samples that comprise your symbol, spread between multiple adjacent FFTs. And if that happens, then you get incorrect data. Now, let's illustrate what that looks like. If you look at rows 39 and 50, you can see that visually it's almost impossible to tell which of those 2 readings represents the symbol. You see there are 2 different values that are really powerful. That's the result of basically half of the samples from one chirp, and basically half of the samples from chirp n, and then half of the samples from chirp n plus 1 wind up in the same FFT. So when we do it, we get those 2 components in there, and it's really ugly and hard to work with. So we can solve this by using a technique called overlapping FFTs when looking for our SFD synchronization. And basically what that means is we're going to process each sample multiple times with the effect of getting better resolution in time of our resulting FFTs. It's more computationally intensive, but it gets us much better fidelity here. So if we do that, this is what the result looks like It's a little bit hard to see right now. I'll get you a better picture in a moment, but basically, it's much less ambiguous in terms of which symbol is present. So if we use those overlapping FFTs, we can synchronize on that SFD, and then once we know exactly where the first symbol of the PHY data unit is in our buffer, we can go back to using non-overlapping FFTs, which are more computationally efficient, and get us this nice read on the right. Here you can see that, again, if we look at lines 38 and 39, that ambiguity is gone, right? You can see exactly where the most intense bin is, and therefore which symbol is present. And here's the whole frame synchronized. So we got the collisions on the left, and it doesn't look that great. On the right, it's much clearer. Cool. So again, we recompute, more computationally intensive, and then we get out our data. Now, one last thing we have to do to wrap up the demodulation. So doing this, again, remember when we were talking about the chirp math, if our chirps aren't perfectly phase aligned, then the resulting dechirp signal might not necessarily be off of the same reference, right? And of course, we don't know what chirp was used to generate the signal on the transmitter. So we have to find some way of normalizing this data to account for that phase discrepancy. And we can do that by referencing the preamble. And it just so happens that the preamble, when you dechirp